going to be r d theta. Okay, could be dx, dy, we learned before, r dr d theta. And I would choose r d theta because it's kind of polar circle with angles. Okay. So I know that p is equal to y squared. So dp over dy is 2y. And q is 3xy. So dq over dx is 3y. This one will be double integral. Let me write d smaller so I have enough room to write. dq over dx is 3y minus dp over dy is 2y. Oh boy, it's easy, huh? dA. And now this is just double integral of y dA. Okay, but I want to change to polar coordinate because I know that this with angle and radius be easier. So it's double integral. Y is r sine theta. I know that dA is r dr d theta. And r is inside the radius, run from 1 to 2. The angle run from 0 to 180 degrees, so 0 to pi. Okay, so you can integrate this. This is what? Integral is separable, right? So what? Of sine theta from 0 to pi d theta times the integral of r squared run from 1 to 2 dr. And this is 1/3 r cubed from 1 to 2. This is cosine of theta, right? Negative, I think, from 0 to pi. Cosine of pi is -1. With a negative becomes 1. And then cosine of 0 is 1, right? And with a negative, so -1, -1 minus negative, 1 minus 1, 1 minus -1. So it's 2 right here. And this is 2. This is what? 8 over 3 minus 1 over 3. I think 2 right here. 2 cubed is 8. 8 over 3 minus 1 over 3. That would be the answer. 7 over 3. So 14 over 3. Yeah. Okay? So, in order to be able to use a Green theorem, make sure that you check for the condition, okay? The curve gotta be close. Okay? And let me start the lecture right here, and I claim that this is pretty good theorems come first, but I claim that later on you find more powerful theorem. I think it's called the Stokes theorem, because the surface right here may not be flat anymore. You can have a surface that's on 3-dimensional space instead of 2, and I claim that it still works. Okay, so later on you may have something like this. Let me erase this and then redraw. Okay, you see, you have some surface like this, and this is your boundary. Instead of integrating a boundary, you can integrate a curvy surface, and that would work as well. But that's for later. Okay, for now, just Green theorem on the flat surface. And instead of doing the integral on the boundary, you can integrate in the interior region of the boundary, and it turns out to be going to be easier. Let me talk about one more thing. It's just an application before I wrap up the lecture. Okay. Say you have a closed region. Black marker is going to be better. Okay. You have a closed region symbol. Okay? This is the curve C, whatever it is. And this is the region D, bounded by the curve C, D right here. And question, can you calculate the area of that region? What is the area? Okay? You can use the Green theorem to calculate the area. Okay? The area is going to be the, let me see, double integral would work. The area is going to be double integral of dA, yeah, okay, over the region D. Right, see, little area and then add them up, you have the double area, right? It's 1 right here, that's what it Okay. Okay. So if you want to use the green theorem, you're going to make it look like what? Double integral of dq over dx minus dp over dy dA, right? It means you have to set what? Dq over dx minus dp over dy equal to 1. Calculate this, right? You have this one. Somehow you have to use a boundary. So PQ going to come up, right? So you rewrite this double integral as the green theorem form right here. So this is going to be equal to 1. So you look for the function. What is P equal to? What is Q equal to? Such that dq over dx minus p over dy equal to 1. It's a couple ways, many ways. Actually, I said P is equal to, say, x, for example. Let me see if it works. P equal to y, dp over dy, yeah? Negative y, and then q is equal to 0. Yeah, that works. So dq over dx is equal to 0. dp over dy is equal to what? Negative 1, so minus becomes 1. And it turns out it's easier to calculate, right? Okay? Or there's many ways. How about another way? How about q is equal to x and p is equal to 0. Then dq over dx is 1. And dp over dy is 0. You have it. Okay? Let me see if the book see if any other way. The book shows you another way. Say p is equal to negative 1/2, I think, of y, and p is 1/2 of x, I think. Yeah, so q, I mean. So dq over dx is 1/2. dp over dy is going to be negative 1/2. So with negative dp is going to be positive 1/2. 1/2 plus 1/2 is 1. And what is this doing here with the green theorem? You know that using green theorem, this double integral, now we convert back from the double integral back to the line integral. This, by green theorem, is going to be equal to integral on the boundary. Let me erase this. Same thing on the boundary. See right here. What? P d x and q dy. P dx plus q dy. Okay? And turn out backwards easier. What is p? If you use this k right here, p is negative y and q is 0. Okay. So it's going to be equal to what? Integral of negative y dx, not because q is 0. Or you can use this one right here, q is x and p is 0. Q is x, is integral of x dy. Right? You can calculate the area. Or use the third one right here. It's going to be integral of negative 1/2 y dx plus 1/2 x dy, and integrate. Anyway, you get to the answer. And this is one of the applications of calculating the area bounded by the curve C. And the double area shows you backward, right? Double area sometimes is hard, so what do? You convert from double integral back to the line integral, and you integrate around the curve. And that's 3, but not all, okay? You can find more ways. It's just that what dq over dx minus dp over dy equal to 1, if the function works. And that's the way to solve the problem. And this is the end of this video clip today. Thank you for watching, guys. And it's getting harder, right? Any question, please feel free to ask. Oh, by the way, if you ask, please check out my email on the syllabus. All right, that's the only email that I will receive the answer, and it will be safe in the school system. Thank you very much, and have a good day, everyone. Bye-bye.